Okay. Why is the cost function concave? In fact, I'm going to prove, everybody agrees this is kind of like, that one's a pretty easy one. Everybody would agree this one's kind of pretty easy too. So the only two that are kind of tough are really these two. This one and this one. Right? Those are the two that are sort of tough. And that's what we're going to prove right now. Okay? And I'm going to prove it first in kind of a graphical way that'll show you the logic behind why it's concave. And then we can come back in a minute and prove it more broadly. So I want to think about it in a unidimensional case. And you could actually think of it as a multidimensional case. You just would have to be moving along some vector, but I'm not going to care about that. I'm going to think about, here's the price of good J. And in my experiment, the only thing I'm going to be moving is the price of good J. And I'm going to start out at some Pj naught. That's the initial price. So I got Pj naught and P1 naught all the way up to Pn naught. Right? I got all my prices got some initial number. And I'm going to assume that I have some cost at that initial point. So this is some cost minimizing point. This is C of P1 naught up to Pn naught U bar. That's my cost. Okay. And I know that point. That's my starting point. And then I'm going to say, how does my cost vary as Pj moves? As Pj changes, how does my cost vary? Okay? And I want you to consider a kind of stupid solution. Okay? This is like the monkey solution, right? This is like I'm not thinking at all. As the price of good J changes, I'm not going to do anything. I'm not going to change my bundle at all. Now, that's not the optimal response. Everybody would agree. Could be the optimal response, typically not. Right? So as an initial starting point in my mind, I'm going to say, how would my cost vary with Pj if I didn't change my decision at all? Well, what would happen? Well, I would move straight along a line, right? I would move along a line that would be linear in P. Like say I'm consuming 10 units of good. Say at this point I'm consuming 10 units of good J. Then for every dollar I raise the price, how much is my cost going to go up? $10. I'm going to 10 units, and every dollar the price goes up, I pay $10 more. And every dollar the price goes down, I'm going to save 10 bucks. But he agrees with that. So I would be moving along a line, and the slope of that line equals xjh of P1 up to Pn naught U bar. So if I didn't do anything to adjust my bundle, I would move along that line. And that line has slope equal to the Hicksian quantity. It's also equal to the Marshallian quantity, by the way. It's equal to the quantity, right? It's 10 in my example, which is both the Marshallian quantity and a Hicksian quantity. Okay? So whatever that quantity is, I would move along that line. Now, if I adjust my bundle, if I make an adjustment to my bundle, I can't do any worse than this. Right? This is the worst I could do. I mean, the optimum got to be at least this good. Because the best solution is always better than the stupid solution, right? It's got to be at least as good. Therefore, my cost function has to be below both on the left and below on the right. All right? So now you see the logic. It has to have that slope precisely because, it has to be concave because the worst case would be linear, right? If you couldn't adjust at all, it would be linear. If you can make some adjustment, it's going to only adjust to make it concave. But we also now get an idea of how concave it's going to be. If the optimal adjustment is strong, that I'm able to adjust a lot, then this thing's going to be quite concave. Because it's going to have slope 10 at the beginning, and then I go to 9, it's only going to have slope 9. Then I go to 7, and it's only going to have slope 7. Right? It's going to be getting curved. And the more curved it is, the more adjustment this guy must be making. So the idea is, I started with this function that was inherently linear. And by minimizing that function, I'm going to make it from linear to concave. Because I couldn't make it convex. That would be going in the wrong direction. I'd be like doing something stupid. As long as I do something smart, I'm going to move this in to make it concave. And the slope is going to be equal. So that's really what lies behind it. Right? Now you can jazz this up because you could say, look, really let's not start with some just moving just PJ, moving some direction, then same story. Doesn't really matter.